Welcome to today's presentation entitled Fundamentals of Geodetic Kinematics. My name is Dr. Jim Beatty, and I work at the NASA Langley Research Center in Hampton, Virginia. I'm a member of the NASA Engineering and Safety Center's Flight Mechanics Technical Discipline Team. This presentation is part 2 of a two-part discussion about geodetic kinematics and is sponsored by the NESC as part of its educational outreach program called the NESC Academy Online, which is a collection of video and audio presentations in a number of technical disciplines of interest to the NASA community. Today's presentation, as I mentioned, is part 2 of a two-part discussion, and today's discussion is entitled Implementation. As an overview of today's presentation, we'll first begin with a review of what we covered in part 1 of this presentation, which was entitled Introduction and Definitions. In part 1, we discussed various mathematical relationships for ellipses, which is instrumental in defining the characteristics of oblate spheroids. As you might recall from part 1, an oblate spheroid is nothing more than an ellipse that's been rotated about its minor axis. And so the relationships for ellipses is key to defining some of the expressions we use to transform coordinates between rectangular coordinates or spherical coordinates, which are commonly used. Either one of those are commonly used for defining geodetic kinematics. We also discussed some coordinate frames and definition of terms like what's the difference between geodetic parameters versus geocentric parameters. We presented some of the equations used for geodetic kinematics. And finally, we also presented in part 1 the equations that would be used to transform spherical position coordinates to rectangular and vice versa. In today's presentation, part 2, entitled Implementation, will cover some more detailed implementations of the material that was presented in part 1. First, we'll start off with, again, a discussion or definition of what sidereal time is. It's commonly used in these type applications. We also will provide a summary of World Geodetic Standard 1984 constants that have been defined for the Earth and the Moon. We also will discuss some coordinate frames that are commonly used for geodetic kinematics, the equations for navigating over an oblate spheroid that might be used, for instance, in an inertial navigation software. We'll also discuss how to compute great circle distances, and finally the calculation of position and velocity of an object relative to some planet fixed frame if you have its information in a, say, in a Earth-Centered Inertial frame and you want to convert it to a planet fixed frame for convenience. Sidereal time is the angle in the ecliptic plane between the x-axis of what's called an Earth-Centered Inertial frame, and that x-axis points toward the vernal equinox, and the corresponding x-axis of an Earth-Centered Earth-Fixed ECEF frame, in which case the x-axis of that frame points toward the Greenwich meridian. Recall from part 1 of this presentation, Earth-centered Earth-fixed frames are often also called Earth-centered rotating frames, since they rotate with the Earth, and they are centered at their origin is centered at the center of the Earth or the whichever planet you're discussing. Sidereal time is really an angle, but it changes proportional to time due to the almost constant rotation of the Earth. In this case, the 7.292 times 10 to the minus 5 radians per second. The inertial longitude is the sum of the sidereal time angle and the geodetic longitude, which the geodetic longitude refers to the longitude relative to the Greenwich meridian on Earth. The initial value of the sidereal time of a trajectory is dependent on both the date and the time of day at the beginning of that trajectory. And for those of you who might be users of the program to optimize simulated trajectories 2 or post 2, it can be used to compute sidereal time for a given day and time. And I'll discuss that on the following slide. Other applications, I'm sure, have similar capabilities for computing sidereal time. Here's just a brief example of an input deck that could be used to compute sidereal time for a given day and date and location on the Earth. I won't go into the details here, so if you're not familiar with POST, you can get access to some of the documentation for what these inputs mean. But primarily what's shown here is I've entered down under the comment called initial position, the geodetic latitude and longitude that correspond to launch area, Launch Complex 39B at Kennedy Space Center in Florida. And then just below there under the comment set launch date, I've set the month to August, or the 8th month of the year. The day is the 15th. The year is 2009. And then there's a parameter called NPC31 that sets how to calculate the ephemeris data. We've set it to an option of 1, which calculates 0-hour ephemeris at using the 1950 model. So the way this is set up is we'll set this to be just a single pass run through post. In other words, it'll run just one time and compute an output file. You'll notice under the final statement there where it says PRNT1 equals GHA, we've added the Greenwich hour angle parameter, which is an output from post, into the output list. And it's the Greenwich hour angle in degrees, and it represents the sidereal time at Greenwich, England at midnight on the date specified, or the 0 hour on the date specified. So down at the bottom of the slide shows an example of how you would take the Greenwich hour angle calculation that's output from post and use it to compute the sidereal time. First, you would extract from the output listing the value of GHA for this scenario that you've put in, and you would find if you did this, it would have returned a Greenwich hour angle of 323.53667 degrees. So to convert that from midnight at Greenwich, England to 7 a.m. at Kennedy Space Center in Florida, you would add 11 hours to that calculation, which is 7 a.m. plus the 4-hour time distance from Greenwich Mean Time to Eastern Daylight Time, since August is in Daylight Savings Time period. If it were not in Daylight Savings Time, you would add 5 hours to it. Then you would multiply by the angular rate of the Earth, which we discussed earlier. That was presented in radians per second, but since we're operating in degrees here, the corresponding Earth rate in degrees per day is 360.985605 degrees in a 24-hour period, then divided by 24 hours per day. And then if that calculation results in an angle greater than 360 degrees, you would subtract 360 from it, so that it puts it in the range of 0 to 360 degrees. So following through all those calculations, you would take the 323.53667 degrees for Greenwich hour angle out of post, add to it 11 times 360.985605 degrees divided by 24, and then finally subtracting 360, you would find that you'd get a sidereal time at 7 a.m. on August 15, 2009 at Kennedy Space Center of 128.982 degrees. And that would be the angle that you would use if you were constructing a trajectory beginning at that particular time and date. The World Geodetic Standard 1984 is defined in a couple of documents and it's a widely used standard for definitions of oblate spheroid representation of the Earth, and it also includes quite a bit of other information that we won't cover today, such as the gravity constants that are used, and a number of other things related to tidal effects and things like that. But I've included in this presentation links to a couple of more important sites. The first one there is the WGS84.pdf file. It's a PDF file of the reference standard. And the parameters that it defines are the things that we discussed in part 1 of this presentation, the characteristics of ellipses that are important for computing geometry and kinematics over an oblate spheroid, in particular the Earth. It defines the following parameters to the exact precision as shown, so that if you are working with other people, as long as you use the parameters as defined in that standard, the results will be equivalent. The semi-major axis length, referred to as A in my previous presentation and throughout this one, is listed as shown as 6,378,137.0 meters. The reciprocal of flattening, which is, as we talked earlier in part 1, can be related to the eccentricity, is as shown. The Earth rotation rate, which we discussed earlier in radians per second, is shown. And from these parameters, all the other parameters that you need for doing calculations of geometry over an oblate spheroid can be derived. As mentioned earlier, in part 1 we discussed the equations that can be used to do that those translations. In particular, you can calculate the square of the eccentricity as 1 minus the quantity 1 minus flattening squared. And if you work the math out, you'll see that you get the number as shown there. The semi-minor axis length B can be computed from the semi-major axis length A as B over A is the square root of 1 minus eccentricity squared. So again, carrying out that math, you get the semi-minor axis length B to the precision listed there. And a summary of the key constants that you would find in the World Geodetic Standard 1984 document are shown here for the Earth, and similar constants for the Earth's moon. And then again, as a way of summarizing, given the semi-major axis length A and the reciprocal of flattening F, you can compute the following parameters: eccentricity and semi-minor axis length B from the simple expression shown. And again, these were covered extensively in part 1 of this presentation. Next, we'll discuss some of the typical reference frames that are used in geodetic kinematics. There are several types that can be used. You can have, as we discussed briefly a few moments ago, you can have planet-centered inertial frames, which means the origin of that frame is located at the center of the oblate spheroid and it remains inertial. You can also have planet-centered rotating, which again, it has the origin of the frame at the center of the oblate spheroid, but it rotates with it. You can also define planet relative instantaneous local level frames that their origin may or may not be located on the surface of the planet. Typically they are, but sometimes, as I'll discuss in a moment, they can be located at the where the object is itself, which is above the surface of the planet. The local level frame is characterized as it normally has two of the axes or in a plane tangent to the surface of the planet, again usually directly below the object you're tracking. And the third axis is usually pointing either up or down relative to that local level direction. That means up or down means perpendicular to the surface of the oblate spheroid along a local plumb line direction. And common examples of local level frames that are used for geodetic modeling are northeast down frames, east-north up, azimuth base frames of different flavors, and plumb line frames. And some of these, depending on the application and the user's definitions, sometimes these local level frames could be inertial and sometimes they rotate with the planet. So it just depends on the application and what your needs are. A northeast down frame, from its name, implies that the x-axis points north, the y-axis points east, and the z-axis points down. And you can define a quaternion for defining that orientation of the northeast down frame relative to the Earth-Centered Inertial frame, as we'll discuss here. If you're not familiar with quaternions, please see another presentation that I have provided for the NESC Academy online on quaternions. It's a two-part presentation that discusses in detail how you use quaternions and examples such as this, how you would define a coordinate frame orientation with a quaternion. So assuming you are familiar with quaternions or have reviewed that presentation, you can define the quaternion for this Earth-Centered Inertial to northeast down frame as the product of two quaternions. The first quaternion represents a rotation of geodetic longitude lambda sub e plus sidereal time lambda sub g about the z-axis, and is shown there. Again, just a recap of quaternions. The scalar part of the quaternion is cosine of the angle, rotation angle divided by 2. The vector part of the quaternion is sine of the rotation angle divided by 2 times the unit vector in the direction of the rotation. In this case, the unit vector would be 0, 0, 1, since you're rotating about the z-axis. The second rotation that would be needed to orient that northeast down frame relative to the Earth-Centered Inertial would be a rotation of minus 90 minus geodetic latitude about the rotated y-axis. And it would be shown as represented there by the quaternion Q2. And finally, the ECI to northeast down quaternion would be just the product of Q1 times Q2. And note that that ECI to NED quaternion is also nothing more than a yaw, pitch, roll Euler angle sequence, with the yaw angle equal to the geodetic longitude plus sidereal time. The pitch Euler angle is minus 90 minus geodetic latitude, and the roll angle would be 0. So if you're not familiar or comfortable working with quaternions, you can also just define that as a yaw, pitch, roll, Euler angle sequence. If you desired the northeast down frame orientation relative to the Earth-centered, Earth-fixed, again also referred to as Earth-centered rotating frame, instead of the Earth-centered inertial, you would just replace in the equation above the parameter lambda e plus lambda g with lambda e itself. In other words, just the geodetic longitude without including the sidereal time in that first rotation angle. And shown to the right is just a depiction of what the orientation of the northeast down frame would look like in the context of the parameters defined for geodetic kinematics presented in part 1 of this presentation. Another common local level frame that is used in geodetic kinematics is the east-north up frame, and this particular frame is preferred by many of the people who do inertial navigation software. This frame again is a local level frame with, in this case, the x-axis is pointed east, the y-axis pointed north, and the z-axis is pointed up. And again, it can be constructed as a quaternion with the first rotation of the quaternion is the sum of the lambda e, or geodetic latitude, the sidereal time, lambda sub g, plus 90, followed by a second rotation of 90 minus geodetic latitude about that rotated x-axis. And then the quaternion for orienting that east-north up frame relative to the Earth-centered inertial frame would be the product of the two quaternions defined above as Q1, Q2. And also, again, note that the quaternion for the ECI to east-north up local level frame is also just a yaw, pitch, roll Euler angle sequence, where in this case the yaw Euler angle would be geodetic longitude plus sidereal time plus 90 degrees. The pitch Euler angle would be 0, and the roll Euler angle would be 90 minus geodetic latitude. And again, if you wanted that orientation of the east-north up frame relative to the Earth-centered, Earth-fixed instead of the Earth-centered inertial, you would simply replace lambda e plus lambda g plus 90 with lambda e plus 90. That is, you would not include the sidereal time in that first rotation angle. Next, we'll cover plumb line frames. The plumb line frame is defined with its x-axis up. The z-axis has been rotated through some azimuth angle about north relative to that negative x-axis, and the y-axis completes a right-handed frame. You can define a quaternion elements for a plumb line frame relative to the Earth-centered inertial frame as follows. It's first a rotation angle of geodetic longitude plus sidereal time about the z-axis, as shown as Q1 there. The second rotation angle is the rotation of negative geodetic latitude about that rotated y-axis. And the third rotation is a rotation of the negative azimuth angle about the rotated x-axis. So finally, the quaternion representation of the ECI to plumb line frame would be the product of the three quaternions Q1, Q2, and Q3 as shown in the order shown. And note that again, that ECI to plumb line quaternion is also nothing more than a yaw, pitch, roll Euler angle sequence, where in this case the yaw Euler angle is the geodetic longitude plus sidereal time. The pitch Euler angle is the negative of the geodetic latitude, and the roll Euler angle is the negative of the azimuth angle. And as before, if you wanted the orientation of the frame relative to the Earth-centered, Earth-fixed instead of the Earth-centered inertial, you would merely replace the sum of the geodetic longitude and sidereal time with just the geodetic longitude. That is, do not include the sidereal time in that first rotation. Next, we'll discuss some of the equations that are used for navigation over an oblate spheroid. Quite often, in applications such as inertial navigation, you would use the estimated velocity of some object relative to a local level frame to obtain the geodetic latitude and longitude and altitude, and by computing and integrating the time derivative of those parameters. So they would be initialized at some starting point, and then afterwards, as the vehicle moves around over the oblate spheroid, those parameters would get integrated. The rate of change of those parameters would be integrated, and result in the current states of those particular parameters. Sometimes the local level frame to which you're doing these calculations is attached to the rotating planet at some convenient point, like the launch point, and would just stay there. Other times, however, the local level frame would be located on the surface of the Earth directly below the vehicle's center of mass, and it would move along the surface as the vehicle moves. Sometimes that local frame would be located at the vehicle's center of mass and translate with it, but it would remain oriented so that its x and y axes are still parallel to the plane tangent to the surface that's directly beneath the vehicle's center of mass at any time. And on the next slide, we'll discuss how you would compute the time derivatives of geodetic latitude, longitude, and altitude for such a local level frame. The figures at the right show a meridian view on the top and a top view as the lower figure for the geometry that we're going to discuss now. The meridian plane is a slice through a local meridian containing the object O, which is located above the oblate spheroid, and a point P, which is directly beneath the object that you're tracking or discussing. The lower figure is a top view looking down the z-axis or down the axis of rotation of the oblate spheroid. And the parameters that are shown there were defined in part 1 of this presentation, such as the parameter rho, which shows going from a little plus sign somewhere in the interior of the oblate spheroid up to the point P. That's the radius of curvature in a prime meridian. And rho v is a rotation of curvature in a prime vertical, and rho xy is a parameter that's derived from those two. And those were discussed extensively in part 1 of this presentation. The velocity components of that object in the northeast down frame are referred to as v north, v east, and v down. And as I said, in inertial navigation software, those would be estimated from the state equations that you're integrating. So at any given time, presumably one would know what the estimated north, east, and down velocities are. From those, then, you can compute the time derivatives of the geodetic latitude, geodetic longitude, and geodetic altitude as shown in equations 38 through 40. And again, rho v and rho v are defined in part 1 of this presentation. I'll summarize them here in a moment. And so once the time derivatives of geodetic latitude, geodetic longitude, and geodetic altitude have been computed using these equations, they can be integrated then to propagate the rate of change or the value at any given time in the future. Also, you can compute the rate of change of the angular rates of the northeast down frame, because keep in mind this northeast down frame moves along the surface of the oblate spheroid as the object itself moves around. So then the orientation of that frame is not fixed as defined earlier when we showed the quaternion for how to compute it, but yet it actually moves, or rotates as the vehicle moves. So equations 41A, B, and C are the equations that you would use to compute at any given time what the rotation rate about the north axis is, or the x-axis in this frame, or in this instance, the rotation of the east angular velocity, or the angular velocity about the y-axis of the frame, and finally the angular velocity about the z-axis or the down axis. And again, if you were working with Earth-centered, if you wanted the angular rate of the northeast down frame relative to the Earth-centered inertial frame, instead of using the time rate of change of the geodetic longitude, lambda sub e above, you would use lambda sub e dot plus omega Earth, where you would calculate lambda sub e dot as shown on the previous slide, and then add to it the constant rotation rate of the Earth. And again, just summarize the particular value that you would get out of the World Geodetic Standard 1984 document. The rate of change of the ECEF to NED quaternion, or if you're working in Earth-centered inertial, the ECI to northeast down quaternion would be computed from Poinso's equation. Again, this was presented in part 2 of the quaternion presentation. If you haven't seen that, I would encourage you to review that presentation as well. But in summarizing, the rate of change of the quaternion for the northeast down frame relative to the Earth-centered Earth fixed would be 1/2 times the quaternion value itself multiplied by a quaternion representing the angular rate derived from equations 41, A, B, and C above. And again, those quaternions then can be integrated as well to get the quaternion at any time in the trajectory that you're simulating with the inertial navigation software. Next, we'll discuss how one would compute great circle distances for 2 points on the surface of an oblate spheroid. Because that's commonly needed for navigation purposes if you want to know, how far away is one point from another as you're going over a great circle. And recall, if you don't recall what a great circle distance means, is basically as you're flying from one point to another over the surface of the Earth or surface of any planet, the shortest distance between those 2 points is just a circle that passes through the center of the planet itself. And so you're traveling along what, that great circle as it's called. For a spherical planet, you can actually do exact calculations for the great circle distance, and it's pretty simple to do from the dot product of the rectangular coordinates of each point. So if you were to assume the Earth was a spherical planet, and it's very close to that in actuality, you could compute the surface range over a great circle distance as shown by r surf with the subscript surf. And it's basically just a fairly simple expression in terms of the geocentric, or presented here in terms of the geocentric latitude phi c of points 1 and 2, and the geodetic longitude lambda 1 and lambda 2. However, since our oblate planet is not spherical, it's very close but not spherical, the exact calculations are a little more complicated. But there's actually two simple approximations that are actually pretty accurate. One we'll discuss on the next slide is attributed to Jean Mies, and it's a little more complicated than the one that's shown here. The other alternative is you simply replace the Earth radius in the equation above that corresponds to a spherical Earth with just the average geocentric radius of each of the 2 points that you're looking for. And then once you've computed those using the equations that we described in the part 1 of this presentation for how to compute the geocentric latitude and radius parameters from the geodetic, then you can just simply calculate the average Earth radius as shown as the last equation on this page. And given that average geocentric radius, insert that into the equation at the top of the page for spherical Earth. And it turns out that's actually a pretty accurate calculation. If you want more accuracy with your calculation, you can use this approximation. This is, I said, this normally attributed to Jean Mies. Shown here is actually a little code snippet that was taken from a model that I used. And if you define the A as a semi-major axis length, then it can be in either meters, kilometers, feet, nautical miles, or whatever you want your calculation of the great circle distance to be. Just define that as A in the following calculations. And then it also uses the flattening ratio, defined as F, which again, as we presented in part 1 of this presentation, you can compute the eccentricity from the flattening ratio as shown there. And then if phi sub 1 and lambda sub 1 are the geodetic latitude and geodetic longitude of point 1, and phi sub 2 and lambda 2 are the corresponding parameters for point number 2 that you're looking to compute the great circle distance for, then if you follow the equation shown there, you'll calculate a bunch of constants that are then finally used in the final calculation at the bottom of the page for the great circle distance called DIST. And it's, as I said, just a function of the parameters that are being computed up above. And that's actually a very accurate calculation, even though it is approximate. Next, we'll discuss how to compute the position and velocity of some object relative to some planet-fixed frame. Because, as you may recall, how you normally would use these sort of things is you would integrate Newton's laws in some inertial frame. So, for instance, you might define the velocity or the acceleration of some object in Earth-centered inertial frame, from its forces that are being applied to it. You would integrate that to get the velocity in Earth-centered inertial frame, and then integrate once again to get position in Earth-centered inertial. But quite often you would like to know what's the position and velocity of that object relative to some planet fixed frame, be it a local level frame as we discussed earlier, or some other frame of convenience for your particular application. So what I'll summarize here on the next slide is just the process you would go through, and I won't go into detail these particular steps. You can read them at your leisure, but basically you would just compute the rectangular coordinates of the position of the reference frame origin itself. Then when you compute the velocity of that planet, if it's a planet fixed frame, you'd compute the velocity of that frame caused by the fact that it's sitting fixed to a planet that's rotating. In other words, the Coriolis effect of that frame's rotating relative to an inertial reference. And then you would compute the rectangular coordinates of the object position relative to that planet-centered frame using the equations that were presented in part 1 of this presentation for converting from, if you had your parameters in spherical coordinates, that is latitude, longitude, and altitude, you can convert them to rectangular coordinates as we discussed in part 1 of this presentation. You subtract the position and velocity of the reference frame origin from the corresponding position and velocity of the object itself, and you get the incremental position and velocity of the object relative to the origin of that frame. And then finally, those incremental position and velocities would still be relative to the Earth-centered inertial frame's axes. So then you would want to transform those position and velocity increments from Earth-centered inertial frame to the specific planet-centered frame that you're interested in using, and that would be step 5 as shown there. This is just an example of some MATLAB code that would do the steps that were provided or discussed on the previous slide. Note there's a couple of functions here that are actually functions that I developed that would not generally be available, such as the one shown in the third line down in the coding here, where it's called ECEF, spherical to rectangular. And all that is just a function I developed for MATLAB use that converts spherical coordinates, geodetic latitude, longitude, and altitude, into rectangular coordinates, xe, ye, and ze, or can be xi, yi, zi relative to the inertial frame if desired. Another couple of functions that you'll see down towards the bottom are related to quaternion manipulations. One is a yaw pitch roll Euler's to quat, which basically computes a quaternion for 3 given Euler angles in a yaw pitch roll sequence. There's also a quaternion transform function at the bottom, and most of the time you could find either in toolboxes that are available from MATLAB or Octave or whatever application package. But anyway, this is just an example of the actual equations you'd use to go through and do the steps 1 through 7 that I presented on the previous slide. And the resultant of that would be the final 2 calculations shown at the bottom of this. It would be 2 vectors, RREL NED and VREL NED, and that would just be the RREL NED is the position of the object relative to the origin of the northeast down frame, and the VREL would be the velocity of the object relative to the northeast down frame. And those many times are more convenient to use than the Earth-centered inertial position and velocity components. The next few slides will summarize some of the key equations that were presented and used both in parts 1 and part 2 of this presentation. Shown on this slide are the equations that you would use for converting spherical geodetic coordinates to rectangular coordinates. So if you're given geodetic latitude called phi sub e, geodetic longitude called lambda sub e, and geodetic altitude h of some object, the Earth-centered, Earth-fixed rectangular coordinates can be computed as shown in the 3 equations for xe, ye, and ze in terms of rho sub v, which is the radius of curvature in a prime vertical, and and also rho z, which is the portion of that which is above the equator. And both of those parameters were defined in detail and derived in part 1 of this presentation. If you wanted the rectangular coordinates relative to the Earth-centered inertial frame instead of the Earth-centered, Earth-fixed, you would just simply replace lambda sub e in the equation above with lambda sub e plus lambda sub g, where lambda sub g is the sidereal time, or that is the angle between the vernal equinox and the prime meridian. If you wanted to compute the geocentric latitude and geocentric radius to some point on the surface of the oblate spheroid, depicted by point P in the diagram to the right, or some point above the surface, point O, in the lower figure, the equations shown here would summarize the steps required to do that. The first equation would calculate the geocentric latitude, phi sub c, from the geodetic latitude, the geodetic latitude, phi sub e, again using the eccentricity squared. The second equation shown there for RP would be the geocentric radius to point P, which is the point on the surface directly beneath the object that you're interested in. Finally, the third equation is the calculation for the geocentric radius to the actual point O itself. And the last equation, delta sub 0, is the declination angle of that object. You can also then, once you've computed the declination angle and the geocentric radius, you can use those alternatively to calculate the rectangular coordinates, xe, ye, and ze, as shown in the three equations here. And again, where the geocentric radius r sub c and the declination delta sub 0 were computed as shown on the previous slide. And once again, if you wanted the rectangular coordinates relative to the Earth-centered inertial frame instead of Earth-centered Earth-fixed, you would just replace the lambda sub e in the equation above with lambda sub e plus sidereal time. Now, if you wanted to do the reverse transformation, if you had the rectangular coordinates of some object and you wanted to convert or calculate the spherical coordinates, latitude, longitude, and altitude, these are the equations that you use to perform that calculation. And again, these were discussed in length in part 1 of the presentation as well, but summarized here. So again, if you were given Earth-centered, Earth-fixed rectangular coordinates, called them xe, ye, and ze, and you wanted to compute the geodetic latitude, phi sub e, geodetic longitude, lambda sub e, and geodetic altitude, they can be computed as follows. And note again that was discussed in part 1, this particular formulation uses a approximate solution to compute the geodetic latitude, phi sub e, from a single pass Newton-Raphson technique, and it was also discussed in part 1. That's actually, in general, a more accurate calculation than some of the so-called exact formulations that are available, primarily due to their complexity introducing numerical round-off, even with double precision calculations. So first, to compute phi sub e, the geodetic latitude, you would first compute a parameter, we'll call it theta, just from the first arctangent calculation you see there, in terms of the Earth-centered, Earth-fixed rectangular coordinates xe, ye, ze, and the flattening ratio. Then, once you've computed theta, you can compute geodetic latitude, phi sub e, as the second arctangent calculation shown on the lower equation on the left side above. And in both of those, the principal value arctangent calculation is sufficient for each of those. Then over to the right, the equations shown to the right side of the slide are exact equations for computing geodetic longitude. It's just the arctangent of ye divided by xe, and in this case you do want to use a 4-quadrant arctangent, since lambda sub e can go from plus or minus 180 degrees or 0 to 360, depending on your preference. So once you've computed geodetic latitude from the phi sub e on the equation on the left, then you can use it to compute geodetic altitude, as shown on the lower two figures on the right. And again, the specific equation you would use to calculate geodetic altitude, h, is dependent on whether the resultant location of the vehicle results in a geodetic latitude equal to plus or minus pi over 2, or in other words, is the object located at the north or south pole. If it is not located at the north or south pole, you can use the upper equation, h equals square root of xe squared plus ye squared divided by cosine phi e, etc. Or if the object is located at the north or south pole, you'd use the alternate equation shown below. And again, once again, if you wanted the rectangular coordinates relative to the Earth-centered inertial frame instead of the Earth-centered, Earth-fixed, you would just simply substitute in the equations above the xi, yi, zi rectangular coordinates, which are then the rectangular coordinates relative to the Earth-Centered Inertial frame instead of their ECEF counterparts, and then you would calculate from that, instead of geodetic longitude lambda sub e, you would compute basically what's the sum of geodetic longitude plus sidereal time. The summary of the navigation over an oblate spheroid that we presented earlier, these would be the state equations that you could use to compute the rate of change of geodetic latitude, longitude, and altitude, and also the geodetic, the rate of change of the quaternion that orients the northeast down frame relative to the Earth-centered Earth-fixed frame. And by integrating those states, you can come up with, at any time in the trajectory or later time, you come up with the values of the geodetic longitude, latitude, altitude, and the quaternion for orienting the northeast down frame. Well, this concludes part 2 of this two-part discussion about geodetic kinematics. And as an overview or summary, recall in part 1 that was entitled Introductions and Definitions, we covered the following topics: just the basic mathematical relationships for ellipses that is instrumental in computing some of the geometry that's involved. We discussed coordinate frames and definitions of terms such as what's the distinctions between geodetic parameters and geocentric parameters. We presented some of the equations that were derived and used in those calculations, and finally we presented equations to convert from spherical to rectangular coordinates and vice versa, both in geodetic and geocentric sense. In today's presentation, part 2, which is entitled Implementation, we've covered the following topics as well. We discussed sidereal time, a summary of the World Geodetic Standard 1984 standard constants that are used for the Earth and for the Moon for geodetic kinematics applications. We also discussed coordinate frames that are commonly used for geodetic kinematics, and the equations for navigation over an oblate spheroid, as well as the calculations of the great circle distances for points on the surface of the spheroid, and finally how to compute position and velocity of an object relative to planet fixed frames. I hope you found this presentation to be useful and informative, and I invite you to continue with other presentations that are available from the NESC Academy online. Thank you.